So in today's video we're going to start chapter 6, starting out with 6.1, which looks at the introduction to probability, and then we're also going to do 6.2 today, which looks at the addition rules for probability. So in the introduction, what I just want to look at is what is probability, where does it come from, and the types of experiments that we're going to look at in which we find the probability of something happening. So the first one that I want to look at is a random experiment. What is a random experiment? What are the properties of a random experiment? Okay, there are 3 properties that you have to know. First one is that there is one distinct outcome for each trial that you do in the experiment. So what does that mean? We'll look at that once we've got this written down. Okay, so when you have an experiment, classic examples are always rolling a die, tossing a coin, or picking a card out of a deck of cards. So you can think of any one of those. When you conduct an experiment, let's say that we are tossing a coin however many times, okay? Each time you toss that coin, that is a new trial, okay? But you're going to toss that coin multiple times in order to make up an experiment because you're trying to find the probability of something happening, okay? So each time you toss the coin, it's a trial. So when you toss a coin, you can either have heads or tails, okay? You can't have both, and you can't have something outside of that. So in this case, for each trial, for each toss of the coin, you have one distinct outcome, heads or tails, okay? Second thing is that the outcome of the experiment is uncertain. Okay, if you think about it, when you toss a coin, take a card out of a deck of cards, etc., okay, you don't know what you're going to get. So when you put all of these trials together to figure out the probability of something happening in this experiment, you don't know what's going to come out. You can make a pretty decent guess, particularly with the experiments that we're talking about here, because heads or tails, you know, probably a 50-50 chance or something around that. But you don't know the definite outcome. When you flip a coin, you don't know how that trial is going to turn out. You don't know if you're going to get heads or tails. You can make a pretty decent guess of what the probability of something happening is, but you don't know for certain, okay? So the outcome of the experiment is uncertain. And the third thing, this is more of a definition than it is an actual property, but the set of all possible outcomes is called the sample space. Okay, so when you toss a coin, your sample space would be heads, tails, okay? If you were to roll a die, okay, your sample space would be 1, 2, 3, 4, 5, 6, okay? They're all the possible outcomes. If you were to take a card out of a deck of cards, you would have a list of 52 cards that were in the deck as your sample space. Okay, so the list of all possible outcomes is a sample space, and an event is a set of outcomes. So within that, within your sample space, if I group together some of my outcomes, that forms an event. So for example, you can say, you have a particular problem where it's what's the probability of rolling a 4, 5 or 6 on a die, okay? Well, I'm grouping together the outcomes of rolling a 4, rolling a 5 and rolling a 6, okay? So if you get together a group of outcomes, they form an event. So let's do an example. And again, I'm going to go back to tossing a coin. Okay, so tossing a coin is a random experiment. We've talked about why, we've gone through our properties already. And I said that our sample space in that case, where we're just tossing one coin, okay, the only outcomes that we can have are either heads or tails. This is how we tend to write our sample space. We tend to denote it by S, and then we put it in set brackets. Okay. So now let's do another experiment. So we're going to do the experiment of tossing a coin 3 times. And we want to look at the different outcomes that we can have. Okay. So in this case, our sample space, remember we've tossed the coin 3 times. So when I do that, I could get tails every time I toss the coin. I could get tails, tails, then heads. I could get tails, heads, then tails. I could get tails, heads, then heads. I could get heads, tails, tails, heads, tails, heads, 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 tails, or 3 heads. Okay, so they're all the possible combinations I can get of heads and tails when I've tossed this coin 3 times. Okay, I have 8 possible outcomes. So now I can say, okay, I want to look at the event of getting more than 1 head. So the event of obtaining more than 1 head. Okay, well, let's look at our sample space here. I want to put together the outcomes where I have more than 1 head. So I either have 2 or 3 heads. Well, I can come down here. I've got 2 heads here. I've got 2 heads here, 2 heads here, and 3 heads here. So that event would be tails, heads, 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 tails, heads, 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 tails, and heads, heads, heads. Okay, that's my event because I've put together all the outcomes where I have obtained more than 1 head. So I've just got this set of outcomes. Okay. Let's say that you perform an experiment n times. And within that, the event A, happens K times. Okay, so I'm going to perform the experiment of tossing a coin n times. Okay, and let's say that I got heads K times. Okay, what you then say is that the relative frequency of A, so the amount of times that A happens relative to the overall number of times that I conducted the experiment, the relative frequency of A is K divided by N. Okay, it's very similar to when we looked at relative frequency in our frequency distribution tables. Okay, so our relative frequency, the number of times that the event A happened compared to the number of times that you conducted the experiment, which was N times, is K over N. Okay, now let's say that I conducted the experiment more and more and more times. So N is going to get larger and larger and larger and larger. If you do that and you find the number of times that A happens, and you again find the relative frequency of A for each time when you increase the number of N, and this fraction converges to a number, that number is said to be the probability of the event A happening. Okay, Think about it like where I said tossing the coin, okay? Let's say I tossed a coin 10 times and I got heads 6 times, okay? So my relative frequency of getting heads in that particular experiment was 6/10. Now I'm going to conduct the experiment 100 times. And this time I got 55 heads out of 100, okay? So now my relative frequency would be 55/100, okay? Well, I started out, as I said, let's say I got 6 heads out of 10 tosses of the coin. Then I got 55 heads out of 100 tosses of the coin. And I'm going to keep going and doing this more and more and more times, okay? This fraction here is the same as 60/100, okay? Let's say I now did this again and I did it 1,000 times, and this time I got, I don't know, 510 heads, okay? I'm getting closer and closer and closer to that fraction of 1/2, because I know that half the time I should get heads, half the time I should get tails. But that only happens the more and more and more times you conduct this experiment, okay? Whenever you do one of these experiments, and you could do it by yourself, okay? If you flip a coin, okay? Flip a coin and you get heads or tails. Well, if you only do it 8, 9, 10 times, it's very unlikely that you're going to get exactly half the time you're going to get heads and exactly half the time you're going to get tails. Okay? You normally have to do this experiment more and more and more times to actually see this thing converge to the point where you actually get heads half the time and you actually get tails half the time. Okay? So this is actually called the law of large numbers. Okay, so let's come back to, I'm going to write this over here. So if k/n converges as you conduct the experiment more and more times, this is the probability of the event A. This is actually called the law of large numbers. Okay. And what that says is, as the number of repetitions of an experiment increases, so the more and more times I conduct the experiment, the relative frequency of an event should approach the actual probability. Okay? So that's the law of large numbers. The larger the n gets, the more that this fraction here should converge to the actual probability of the event A happening. I actually have an example here, again with tossing the coin. So let's say we're going to toss a coin, and we've tossed the coin, 1,450 times. Okay? And you get tails 718 times. Okay? So the relative frequency of getting tails is 718 divided by the number of times that we conducted the experiment. Okay? That comes out to 0.4952. Okay? Now we know that the actual probability of getting tails is 0.5. So if I keep tossing this coin so that this number here, 1450, gets larger and larger and larger, I should find that I get some more tails in there as well. So as this number goes up, I should find that this number goes up slightly, and this number should get closer and closer and closer to 0.5. Okay, so the more times you conduct the experiment, the closer you get to the actual probability. Okay, so leading off of that, and this is known as the classical approach to probability, the probability of an event A is, now we tend to denote probability by P, and in parentheses you put A, so it's the probability of the event A. Okay, it's equal to the number of outcomes in A divided by total number of outcomes in the sample space. Okay, let's go back to our original example. Okay, so it's the number of outcomes in A divided by the total number of outcomes in the sample space. Let's come back here. Okay, when I looked at the experiment of tossing a coin 3 times, okay, I had in my event A, which was obtaining more than one head, I had 4 things in that event. I had 4 outcomes in my event, okay, and I had 8 outcomes in my sample space. So in this case, the probability of obtaining more than one head is 4 out of 8. So it's half the time. Okay, it's 4 divided by 8. Now let's do, again, I'm going to go with the same example, but, so I'm tossing a coin 3 times, but I want the probability of getting at least one head. So not more than one head, I want at least one head. Okay. Well, we know, okay, coming back to our example, okay, when we toss a coin 3 times, I have 8 outcomes that I could possibly get, okay, in my sample space. Now I want to look at the number of the outcomes in which I get at least one head. So I've got this outcome, this outcome, this outcome, this outcome, this one, and this one. I get at least one head in every situation other than when I get 3 tails. So therefore my event of obtaining at least one head has 7 outcomes. Okay, there's 7 different outcomes out of the total of 8 outcomes in my sample space. So that means that my probability is 7 out of 8. So the probability of my event A is 7 over 8, which if you work it out on a calculator is 0.875. There are 3 different approaches to probability. The first one is classical probability. That's the one that we're used to. Okay. That means that in an experiment, when you have n outcomes, okay, n possible outcomes, so there's n things in your sample space, then you have a probability of each one happening. Each one is equally likely to happen. And each one has a probability of happening of 1 over n, okay? So for example, with a coin, okay, you have 2 outcomes, heads or tails. And therefore, our probability of heads happening is 1 out of 2, and the probability of tails happening is 1 over 2, okay? With a die, you roll a die, there are 6 possible outcomes. The probability of rolling each one of those numbers is 1 out of 6. You have a 1 over 6 chance of actually getting a 1, of getting a 2, of getting a 3, etc. Okay? Picking a particular card out of a deck of cards. There are 52 cards in a deck, and the probability of drawing any one card is 1 out of 52. Okay? That is classical probability. So, if an experiment has n outcomes, so n things in its sample space. Each outcome has a probability of 1 over n, okay? So they're all equally likely to happen, because every single thing that you have, every outcome that you have, has a probability of 1 over n. So they all are equally likely to happen. There is no one outcome that is more likely to happen than any other one. Like, you're not more likely to roll a particular number on a die than any other number, okay? The next approach is relative frequency probability. Relative frequency probability, if I can say it, relative frequency probability, it's when you do an experiment, okay, and you have no idea going into it what you're going to get out of it, okay? So it's just when we do a random experiment, okay, your probabilities that you come up with are based either off of that experiment that you're going to conduct, or they're based off of some kind of historical data. So I don't go in, it's like when I said like we were tossing a coin 3 times, okay? I don't go in saying each thing has this particular probability like we worked out before. I go in and actually conduct the experiment, let's say 1,000 times, and whatever I come out with from that experiment is what I assume the probability to be, okay? Or I say, okay, well, someone conducted this experiment in the past and this is what they got, okay? So I'm basing, for relative frequency probability, I am basing it off of what I get from an experiment when I conduct it myself, or from historical data. And finally, our last approach is the subjective approach. Okay. The subjective approach is when either you or an expert in the field just uses judgment to assign a probability. Okay, so I could go ahead and say, okay, out of all of my students, I see who is most likely to do their homework. So I can say that a particular person is 90% likely to do their homework tonight based on what I've seen of them before. Okay, so I'm using judgment, what I know about the person and about their character, in order to assign the probability. Or you can get an expert in the field of some particular topic, okay, and they can say, okay, I think, let's say you had someone that was an expert on earthquakes, okay, they could say, okay, I think that it is this likely, there is a probability of this happening, okay? So they can go ahead and assign a probability to something happening, in this case, the probability of an earthquake happening, based on what they know and their expertise. So a subjective approach is when probabilities are assigned just based on your judgment or an expert's judgment. So now let's go ahead and look at 6.2, which looks at addition rules for probability. So the first thing that I want to look at with this is looking at what the probabilities can actually be. So what values can a probability take on? Well, let's look at the probability of an event A being 0. What does that mean? Well, if something has a probability of 0, it means it's never going to happen. So if a probability of A is 0, it means that the event A is impossible. It is never going to happen. Okay. On the flip side of that, if the probability of A is 1, okay? Well, if you've got a probability of something is 1, it means it must definitely happen. Okay, so that means that the event A must happen. Okay, that's like saying what's the probability of obtaining a head or a tail on when you toss a coin? Well, probability of getting heads or tails, okay, is 1, because you have to get at least one of those. Okay, so we know that the probability of an event A being 1 must mean that that event must happen. So between those two values, we can have any probability that we want. So probability of A must lie somewhere between 0 and 1. It can't be negative and it can't be greater than 1, but it can be anywhere inside those. Closer that the probability is to 1, the more likely it is to happen. The closer it is to 0, the less likely it is to happen. Now let's say that you have n possible events. Okay, none of them overlap. Okay, there is no overlap of outcomes between these events, but there are n of them. Let's say that each one of these events was each number that you roll on a die. So you have 6 events: rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, rolling a 6. There is no overlap in those outcomes. They are completely disjoint, but we have these 6 events. So we're going to label them A1 through AN, or in the case of rolling a die, they would be the events of rolling a 1, 2 through to rolling a 6, so there would be A1 through A6. Then the probability of A1 plus the probability of A2, adding together all of their probabilities, must be 1. So you have these n possible events, but they are disjoint. There is no overlap between them. Okay? Then each of their probabilities added together must be 1. Think about why. Well, take rolling a die again. Okay? You have 6 possible events: rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, or rolling a 6. Okay? The probabilities of each one of those happening is 1 over 6. If I add all of those together, there's 6 of them. If I add 1 over 6 6 times, I get 1. Okay? Think of it logically, okay? You must land on one of those events, okay? There are no other possibilities. So the probability of landing on one of those is an absolute definite. You have to land on one of those 6. So if I add all of those probabilities together, I have a 100% chance of landing on one of them. So if I add the probabilities together, I should get 1. A compound event is another type of event that we need to look at. So a compound event is just an event that combines 2 or more other events. Okay. Think about, again, we'll go back to tossing a coin 3 times. And we look at the event of getting at most 2 heads. Okay. So we've got an event here of obtaining at most 2 heads, but that particular event has combined the events of getting no heads, of getting 1 head, and the event of getting 2 heads. I've combined 3 different events into this one event. Okay, so I've got the outcomes of each one of my individual events of getting no heads, one head, or two heads. I've combined those events to create this compound event of getting at most two heads. Now I want to go through something that you have probably seen before, but we need it in order to look at the addition rule for probability. So the first thing I'm going to look at here is the union and the intersection of two events. You have probably seen this before, and I'm going to do this using a Venn diagram because it's way easier to see what's happening. So if I'm looking at the union of events A and B, what does that mean? Let's say I'm going to draw this circle here, and this contains all of the outcomes that are in event A. Okay, so let's say this event could be rolling a 3 or above on a die, okay, and it contains all of my outcomes that I could get within that circle. And then I'm going to come up with event B, which could be, let's say, rolling a 4 or above on a die and all of its outcomes. That's going to be my event B. On the outside, I have my sample space. So within this box, I have all possible outcomes. Within the first circle, I have all of the outcomes in that sample space that fall in event A. And within my second circle, I have all of the outcomes that fall in event B. Now, normally when you conduct an experiment like this and you're looking at different events, you normally have an overlap. So for example, rolling a 3 or above on a die and rolling a 4 or above on a die, well, you've got some overlap there. Okay, rolling a 4, 5 or a 6 is in both of those events. So you normally have some kind of an overlap where these two circles will overlap because there will be overlapping outcomes. Okay. The union of events A and B is just all of the outcomes that fall in A or B or both. Whenever you see the word union, think of the word or, okay? It's all of the outcomes that fall in the event A or in the event B or in both events A and B, okay? So it's all the outcomes that fall in either one of those circles or both of them. On the flip side of that, we have the intersection. Of events A and B. Okay. Again, I'm going to draw my sample space of all possible outcomes. So all of my outcomes for my particular experiment are within that box. Within this circle here, I have all of the outcomes in my sample space that are in event A. And in this circle here, I have all of my outcomes that are in event B. Okay, and again, we're going to say that there's some overlap. The intersection of the two events is just all of the outcomes that fall in both event A and event B. It's just the outcomes that fall in this middle part here. Okay. So whenever you see the word intersection, think of the word and. Okay, so for union, they can fall in A or B or both. In the intersection, they just fall in A and B. Okay. Just as some kind of notational thing here, when you talk about the union of A and B, it's denoted by A union B. So it's got a U in the middle. And for the intersection, it's A intersect B. And you would list the outcomes that fall in either the union or the intersection. Okay. My advice to you is whenever they give you a union or intersection problem is that you draw it out. So you draw yourself a Venn diagram like we have here, and you list all the outcomes in each of the circles that fall in A, that fall in B, and that fall in both, and you're going to list them all in the Venn diagram. Then you can look at the actual outcomes that are in the intersection or the union. Okay, so my advice is to always draw yourself a Venn diagram in this case, and then you can go ahead and actually list out the outcomes for any particular union or intersection. Another thing that you need to know is something called the complement of an event. Okay, the complement of an event A is just all of the outcomes that are in my sample space but are not in my event A. And then inside that, I have my outcomes that fall in event A. Then the complement of A is just the set of all the outcomes in my sample space that are not in my event A. So I'm actually going to draw this slightly differently. This is going to be my event A, and then anything that falls in my sample space, any outcome in my sample space that is not in the event A is in the complement of A. And it's actually denoted by A with a superscript of C. Okay, so it's all the outcomes in my sample space that don't fall in my event A. Because of this, okay, we're guaranteed to fall somewhere in our sample space. So the probability of falling somewhere in our sample space is 100%. It's 1. Okay, so because of that, the probability of A plus the probability of the complement of A is 100%, because I'm guaranteed to either fall in here or to fall in the outside of that, but I'm guaranteed to fall somewhere in my sample space. So the probability of A plus the probability of the complement of A should be 1. So therefore, if you ever need to find the probability of the complement of A, it's just 1 minus the probability of A. Another term to know is mutually exclusive. So two events are mutually exclusive if they have no outcomes in common. Okay, so if they have no outcomes in common, so if event A and event B have no outcomes in common, that means that there is no overlap in that Venn diagram. So let's come back to here, okay? If events A and events B are mutually exclusive, they have no outcomes in common, which means that there is no overlap to these two circles. So the Venn diagram would actually look something like this. Okay, they're completely separate. There is no overlap. So because there is no overlap, A intersect B has nothing in it. There is nothing in the intersection of A and B because they don't intersect. They don't overlap. So that means that A intersect B has nothing in it. It is the empty set. That's how we denote that, okay? When something has nothing in it, we say that it is the empty set. So therefore, if there's nothing in that particular set, if there is nothing in A intersect B, there are no outcomes in there. Therefore, the probability of A intersect B is 0. Okay, there is no way that that is ever going to happen. Therefore, for mutually exclusive events, let's come back to our union Venn diagram. Okay, the probability of A union B, okay, if there is no overlap, then the probability of A union B would just be the probability of A plus the probability of B, because we don't have to worry about this overlap. So the probability of A or B happening is just the probability of A happening plus the probability of B happening. This only works if they are mutually exclusive. If there is an overlap, this formula does not work. But it does work when they are disjoint, when they are mutually exclusive. So this leads us to the general law of addition. Okay. And that tells us that for any two events A and B, this formula will hold. And this is a formula that you're going to have to remember. Okay, so the probability of A or B happening, okay, so this is the probability of A or B or both of them happening, is equal to the probability of A happening plus the probability of B happening minus the probability of both A and B happening at the same time. Okay, so why is that? Again, let's go back to our Venn diagram. Let's look at this union here. So the probability of A or B or both happening, okay, is equal to the probability of A happening, so it's the probability of any one of the outcomes in A happening, plus the probability of any one of the outcomes in B happening. But when we have done that and looked at the probability of A plus the probability of B, you will have noticed when I drew those circles that this inside part was counted twice. It was counted both within the probability of A and within the probability of B. So that inside part is just the intersection of A and B. So if I do the probability of A plus the probability of B, but then subtract the probability of that intersection happening, I take away that extra intersection that I have counted when I've counted this twice. Okay, so when I looked at the probability of A and then the probability of B, this inside part was counted twice. So if I subtract the probability just once of that happening, of the probability of A intersect B, then I'm back to just counting that inside part once. And I then am fine and don't have to deal with counting it twice. So that is where this comes from, okay? Think of it in terms of that Venn diagram. It also agrees with mutually exclusive events, okay? Remember that for mutually exclusive events, probability of A intersect B is 0. So then we are just left with the probability of A union B is the probability of A plus the probability of B. So this still goes back to what we have for mutually exclusive events, but this law works for any events A and B. Let's do a quick example. Okay. This says, suppose that a marketing manager mentioned earlier believed that the probability that someone earns more than $50,000 is 0.2. So probability of earning more than $50,000, there's 0.2 chance, and the probability that someone will subscribe to more than one sports magazine is 0.3. So probability of subscribing to more than one sports magazine is 0.3. If the probability of finding someone that both earns more than $50,000 and subscribes to more than one sports magazine is 0.08, so the probability of falling into both of these categories is 0.08. What is the probability of finding someone who is earning over $50,000 or subscribe to more than one sports magazine? So we've got the probability of one event happening, we've got the probability of a second event happening. And then they've given us the probability that someone falls into both of those categories. Okay, so they have the probability of earning greater than 50,000 and the probability of subscribing to more than one sports magazine. Okay, so the probability of being in both of those categories is 0.08. We want to find the probability that either one of these is true. So they're either earning more than $50,000 or they subscribe to more than one sports magazine. They don't necessarily have to fall in both categories. They just have to fall in at least one. And we want the probability of that happening. Okay. Again, whenever you see the word and, you're looking at the intersection. Whenever you see the word or, it's asking for the union. So I'm looking at the probability of earning more than $50,000, which I'm going to call event A, or subscribing to at least one or more than one sports magazine. Okay, so I've got the probability of earning more than $50,000 or subscribing to more than one sports magazine. I don't necessarily have to be in both categories, so I know that I'm looking at the union. Will equal the probability of earning more than $50,000 plus the probability of subscribing to more than one sports magazine minus the probability of earning more than $50,000 and subscribing to more than one sports magazine. So I should get 0.2 plus 0.3 minus 0.08, which comes out to 0.42. Okay. So remember, if you see the word or, we're looking at the union. If we see the word and, we're looking at the intersection. So they've told us the probability of being in both of those categories, of earning more than $50,000 and subscribing to more than one sports magazine. They've given us that probability, so we know that we have the probability of the intersection. We're looking at finding the probability of the union, of falling into one category or the other category, but you don't necessarily have to be in both categories. The last thing I want to look at is kind of like a side note here, and it's looking at odds. Okay, whenever you see, like, you see it on TV with like horse racing or anything, any kind of sport where they look at the odds of someone winning something. Okay, this is actually done using probability, as you may have guessed, but they're always done kind of weirdly. So it's like the odds are 5-1 or 3-2, and they look weird, like a ratio type thing whenever you see it. What does that actually mean, and how can you actually calculate a probability of something happening from like betting odds? Okay, there is actually a way to do it, and I'm going to go through that because it's actually kind of an interesting thing for whenever you do come across it. Okay, so let's say that we're looking at the odds of a particular horse winning a race. Okay, so odds of a horse winning a race. Okay, whenever you see that, it's normally done as like 5-1, and it will look like that. Okay, I'm not actually going to use this example here, but I'm actually going to use different odds. But that's what it tends to look like. Okay, question is, what does this mean? Well, the odds in favour, there's the odds in favour and there's odds against. The odds in favour of an event A, so the odds in favour of someone winning, is the probability of A divided by the probability of A complement. The odds against an event A, so the odds against someone winning, actually the other way around. It's the probability of A complement divided by the probability of A. So let's look at how we get from probabilities to odds, and then we'll look at how we get from odds to probabilities. So if the probability of an event A is 0.4, okay, that means that the probability of A complement, the probability of A not happening, is 1 minus the probability of A, which is 0.6. Remember that the probability of A and the probability of A complement have to add to 1. So the odds in favour, okay, I've got my probability, let's say the probability of a particular horse winning is 0.4. They have a 40% chance of winning. How do I find the odds for that horse to win? Okay, so the odds in favour of that horse winning are the probability of A divided by the probability of A complement, which is 0.4 divided by 0.6. If you plug that in, you can plug it into a calculator if you want to simplify it. If you multiply top and bottom by 10, you get 4/6, then divide by 2, you get 2/3. Okay, so that fraction simplifies to 2/3. So that means that my odds in favour are 2 to 3. Okay, the odds against that horse winning, odds against are the probability of A complement divided by the probability of A, which is 0.6 over 0.4, which simplifies to 3/2. So the odds against are 3 to 2. Okay. So we can see, given a probability of this particular horse winning being 0.4 or a 40% chance of winning, we can actually find the odds. That's where this comes from. That's where these odds come from. We can also work backwards. So if you are given the odds in favour or odds against of someone winning, okay, so let's say that we were given these odds here. To find the actual probability, so if they gave you these odds on a TV and you had to work backwards to actually think about what the probability of that particular person or that particular horse winning a race, okay, you actually had to find the probability given the odds, you can actually go backwards. So if odds in favour are written as n to m, so 5 to 1, 2 to 3, whatever that might be, then the probability of the event A actually happening are n over n plus m. So, for example, if the odds are 2 to 3, then the probability of A is just 2 over 2 plus 3, which is 2/5, which comes out to 0.4. So you can go backwards on this, okay? So you can, given the probability, you can find the odds, and given the odds, you can now find the probability. So given the odds, we can see with odds of 2 to 3, they have a 40% chance of winning, okay? That's just a side note. You don't need that for your homework. It's just kind of a cool side note of like what we've just done and looking at probabilities and where it can actually be used in other areas of life. You should be able to now go ahead and do the 6.1 and 6.2 homeworks. As I said before during the video, whenever you deal with unions or intersections, my number one piece of advice is to draw this out using a Venn diagram. Okay, Venn diagrams are going to be your best friend through probability. Okay, always draw out the Venn diagram and write the outcomes within that Venn diagram so you actually know what you're looking at and you know where these outcomes fall. Okay. If you need any help, please let me know and I will see you in the next video.